Lesson number 3 in our unit on transformations is on symmetry. Let's start with line symmetry. A figure has line or reflectional symmetry if the figure can be mapped onto itself by a line of reflection. Sounds familiar, like reflections, like we did on day 1. So think of a mirror image, it says here. Okay, here's an example for us. So does this triangle here have a line of symmetry? Well, we're going to assume that since these two sides here appear to be congruent, that they are congruent, which means yes, I do have a line of symmetry, and it's right there. If this were on a piece of paper and I folded that triangle right on that line, then the two parts of the triangle would be right on top of each other. So this triangle has line symmetry. What about point symmetry? A figure has point symmetry if the figure can be mapped onto itself by rotating the figure 180 degrees about a point. So in other words, if you can take a figure and turn it upside down and it maps right onto itself, it has point symmetry, just like this letter N here. If I rotated this N right about that point, 180 degrees, it would look just like it does now. Can you think of any other capital letters of the alphabet that the same could be said of? How about this one? How about H? I think so. Point symmetry. Right there would be our point of rotation. Any others? Might be a good thing for you to ponder. All right, what about rotational symmetry? A figure has rotational symmetry if the figure can be mapped onto itself by rotating the figure less than or equal to 180 degrees about a center point. So this sounds like point symmetry, and there is a little rule that I want to tell you here. If a figure has 180 degrees point symmetry, then, I'm sorry, not point symmetry, rotational. If I have 180 degree rotational symmetry, then this figure also has point symmetry. So you see what we said about point symmetry. If I can rotate the figure 180 degrees and it maps onto itself, it has point symmetry. Rotational symmetry can be less than or equal to 180. So if I know I got 180 degree rotational symmetry, then I definitely have point symmetry. But let's take a look. We can have other rotational symmetries besides 180 degrees. Let's look at this little pinwheel here. Let's see what rotation I would have to do on this thing until it mapped onto itself. So I know that if I took each one of these vertices and turned this far, then it would map onto itself. How do I figure out what that rotation is? Well, I got to find out how many there are and divide that into 360, right? So what do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9. Is that right? So 360 divided by 9. That's not 9, it's 8. 1, 2, 3, 4, 5, 6, 7, 8. 360, that's better. 360 divided by 8 is 45 degrees. So this pinwheel here is said to have 45 degree rotational symmetry, because if I rotate this 45 degrees, then it looks just like it does right now. 45-degree rotational symmetry. So as you can probably imagine, some of our regular polygons will have rotational symmetry. Let's take a look and see. How do I determine if a figure has point, line, or rotational symmetry? Well, let's look at line first. I can see this thing has, if I rotated about this line symmetry, I got two lines right here, right? Oh, maybe more, maybe more. In any case, I have some lines of symmetry. So I definitely have line symmetry. How about point symmetry? Yes, indeed, because if I rotated this figure 180 degrees, it would look just like it does now. Upside down, it's the same as it is right side up. Rotational symmetry. Well, if I have point symmetry, I have rotational symmetry, but what degree of rotational symmetry do we have? How many degrees would we have to turn this thing until it was mapped onto itself? I think we could do it with 60 degrees. Let me clean this up a little bit. When I'm thinking of rotational symmetry and my regular polygons, what I got to think about is the central angle, right? So if I rotate this regular hexagon 60 degrees, then this vertex, let's call it A, it's now going to be A prime. And so the whole thing is going to turn 60 degrees and it's going to look just like it does now. So with my regular pentagons that do have rotational symmetry, I want to check to see if the central angle is how many degrees I need to rotate that thing. So let's look at this triangle, and we're going to assume this is an equal, well, let's see. This doesn't say these figures are regular, but we're going to assume that this is regular and this triangle is regular, which means it's equilateral. So does it have line symmetry? Sure it does. Does it have point symmetry? Does not have point symmetry, does it? Because if I rotate, point symmetry means I have to be able to turn it upside down and it maps onto itself. Not the case here. So I do not have point symmetry. Do I have rotational symmetry? Indeed I do, because once again, look here. If I rotated this triangle 120 degrees clockwise or counterclockwise, then since it is equilateral, it would be mapped onto itself. So I do have line symmetry and rotational symmetry there. How about this parallelogram? Looks like a parallelogram. Do I have line symmetry? I do not. I might want to think that I have line symmetry, but if I sketch this line in here, or the one through the other two diagonals, and I folded this along that line, these two vertices would not map onto one another, nor would they if I use the other diagonal. So I do not have line symmetry. Do I have point symmetry? Let me erase this here so I can take a better look. Point symmetry. If I rotated this 180 degrees, this vertex would indeed map to this vertex. So yes, I do have point symmetry. That means I do have rotational symmetry, and it's 180 degrees. There's no rotation of less than 180 degrees for that parallelogram that I could do that would map it onto itself. How about a right triangle? And this one, it's not isosceles. I'm just assuming it's a regular old right triangle. Does it have line symmetry? Nope. Does it have point symmetry? Nope. If I turn it 180 degrees, it will not be mapped onto itself. Does not have rotational symmetry. So this guy has no kind of symmetry. And how about the star here? Does it have line symmetry? Sure it does. I know that it has line symmetry. Here's a line of reflection, right? I guess there are other lines of reflection, right? This would be a line of reflection. In all these cases, I could fold it on any of these lines, and I would have the star mapped onto itself. So definitely has line symmetry. Does it have point symmetry? Could I rotate it 180 degrees and it would look the same upside down? No. Does it have rotational symmetry? It actually does have rotational symmetry, because if there's my point of rotation, if I rotate this many degrees counterclockwise, or I could go the other direction too, then this star will be mapped onto itself. And if I measure that, 360, that's going to be, I got 5 of those angles in there, right? 1, 2, 3, 4, 5. Yeah, so 360 divided by 5 would give me rotational symmetry of 72 degrees. So that's our lesson on symmetry. We have one more to go in this unit. It is on dilations. So I will see you soon.